Come on. Yeah, come on. I will do something with a learning system. I would like to, yeah, here is place and I can put my what? This is not good. Key. Yes, yes, yes. Yes, I'm able to show my yeah. Same. Remember. And we are on one, so we can do something. Okay, what's on my agenda today? What I'm planning? I would like to speak on line to ground faults. What I'm thinking? Typical general schematics for such end-to-end faults. I can repeat. Its typical schematics is like this. This is common wire for direct sequencing, equivalent EMF for direct sequence, equivalent resistance, equivalent resistance of the direct sequence. Let's say it's connection point of direct sequence. Here will be common wire for the negative sequence, its connection terminal, and equivalent resistance of the negative sequence. Connection between them is a fault resistance if we have a fault, and T moment. If this schematic is for a phase of sequence while modeling fault whatever fault, like this. Will be like this. Is between B and C phase. Such schematics, that easiest schematics corresponds to BC fault. But it reflects, it's mimic of the A phase. Bit strange, isn't it? We have B and C fault, but we conduct schematics for non-damaged phase. Okay, this is general. This at this moment it's kind of blah blah blah. I would like to take as example how to apply this general idea. Very common case. So you have a middle voltage network, 10, 11, 20, 24 kilovolts, whatever. Connection transformer. This is your distribution network. Here we will have most possible delta connection. Ground start connection at a 0.4 kilovolt part. It will be circuit breaker, okay. Maybe automatic switch. So here we have 0.4 kilovolt bus, and we will model BC4 at a load here, maybe at this part. It's a very common kind of fault. And we are considering this fault key, one of the quality criterions of fault protection. Here you will have, let's say, current source, some kind of protective device which will trigger the circuit breaker like this one. Yeah? Have you seen the real circuit breaker? I have one. Idea: this protection should be able to detect this fault and disconnect. It's a must. It's a key, on every good checklist. You will see this. You need to be able to disconnect, detect and disconnect fault at the client side. Because in theory, here is a kind of administrative border. In Latvian, it's piedarības robeža, border of ownership or border of alignment. This part belongs to city network. This part here starts custom. In theory, here starts customer. But client net, we cannot trust customer on our transformer. We cannot trust transformer. So we should be able. What they are doing is their problem, but we should be able to save our transformer. And one more moment, not only save our transformer. This, I draw a nice bar, but it's a part of the huge chain possible. I draw nice switch, but it's extremely possible. But we save money and we have a T connection. Here we don't have protection of the line. If something bad happens here, we lost all this chain, and it will be very bad for our KPI. To simulate such network, what I got, what I got here is a network, rheostats, I got transformer, ampere meters, and this nice black resistor will be a fault resistance. Also, I have active load and my motor. My schematics looks like this. 5 ohm resistance, A, B, C. Here I have 230 volts network. Delta connected primary windings of transformer. On a secondary side, I have prepared what I got. A, B, C. This network is 221 volts. From this came what? Okay, I have ampere gauge in all phase and also in neutral wire, and I have a load active are 300 watt box, and with that switch I have an asynchronous machine connected. Here is my setup. I will create a form with nice red. Okay, it's black, but it's red. With the fault resistance array. And we will see what happens. See, blow, blow. See, it's a mimic of typical client connection to a distribution network. So I need to conduct a mimic schematic in a space of symmetrical components, or I must account all mutual inductance of transformer. I don't like idea of this inductance matrix, so I will use technique of symmetrical component. I need to create two interconnected schematics. One for direct sequence and one for negative or reverse sequence. And connect them as a complex scheme. I just draw on my... So, what we will see? System CMF, resistance, it's, let's say it's R1, it's my 5 ohm resistance. Immediate important moment. I should select a voltage, area of voltage, this voltage level at which I will perform my calculus. I will do it at a fault place, at a fault stage. So these two I will need to reduce them to the voltage of the fault place. with it will be 221 to 230, the scale reduction factor. In your, if in future you will consider something like this, it will be like 10,000 to 0.4. If you reduct to the client voltage. You can also do the trick. You can select the base voltage, let's say 11 kilovolts. So in this case it will be 11,000 or 11 to 0.4. And you will get but in such case this part will not be reduced. See? In real world, this will be at 11 kilovolts and part after transformer at 0.4. So if you decide to perform this reduction to 11 kV, you don't tackle this part, factor will be 1, but you will need to rise part after transformer to the 11. You have two voltage levels or two voltage areas, 0.4 or 10, 11, what's the distribution? Maybe 24. So what it's at 24, if you decide to use 24 as a base, remains intact. 0.4 goes up. Or you reduce 24 to 0.4 and those schematic will be at 0.4. So this, I will mark them with a star, but they will need reduction to the base voltage. What else? Resistance of my transformer. Here will be connection point M1, and this is common wire for direct sequence. Also, what I need to put here, I need load resistance, yeah, and my asynchronous machine, direct sequence resistance of my asynchronous machine. For the negative sequence, I would like to reserve some space for the incidence matrix. Interconnection. Here, what I will see, R1 transformer, this is N2. Okay, what next? My asynchronous machine resistance, but for negative sequence, it's equal to startup or in rush resistance and resistance of my load. And as interconnector, what will be my interconnector? It's a fault resistance. Here is my schematic. Here is my mimic. Will you buy an alarm clock one day? If you cannot program your phone as alarm, buy this large old alarm clock. Yeah. This is a mimic for line-to-line fault at the client side. From the distribution network perspective. What do we need now? We need to put a node. Node 1, node 2, this will be node 3. No, not needed. I will add this as a branch. This will be the same node 2. This will be my node 3, and this will be my node 4, and this can be as a B. 1, 2, 3, 4. Looks okay. Now branches. This will be branch 1. This will be branch 2. Let's say this is branch 3. Branch 4. I will add asynchronous machine bit later. Or maybe this will be branch 5. What I'm doing? This is branch 6. And this one can be 7. I will add later my machine as a branch 8 and 9. Or I can do it immediately. Just for okay, I will add this branch, but I will set resistance to something very big. So this means that it's the same 2 and this the same 3. So 1, 2, 3, 4 nodes. One, 2, 3, 4, 5, 6, 7, 1, 2, 3, 8, and last one will be 9. This will become a topology for our matrix for our network. The first matrix of incidence. Okay, method. Your temp amp method, not some method. Well, so what should I write? So what should I write on position 1? Oh, we have online viewer for some time. Panvar, what's the way? What are you doing? We're studying electrotechnics. What we are doing? So what I'm writing? Position 1, 1. Branch 1 flows in, -1. Other positions will be 0. Okay, what about 1, 2? It's 0. Okay, First dimension. This is dimension 1, this is dimension 2. 1, 2. This element. What I'm writing? Any ideas? What's this? Branch number 2. And what? In or out?
Oh, 1, 1.
Out?
Yep.
Out means 1. And here I'm writing?
0.
Really?
Minus 1.
Minus 1. 0, 0. Number 3. Here it is. What am I writing here?
3, 1. 0.
Number 3. Any connection to the first node?
No.
No. 0. Branch 3, node 2. What do we see?
1.
1. And in flows in number 3. Yeah. Branch number 4. Where are you? One moment. Bit of set. So this corresponds. What? Number 4. Here it is.
Yes.
Flows in number 2, yeah?
Yep.
So here minus 1 and no other connections. This bar is a ground or common wire. No rows for it in my text. Who's next? 5. And what do we see? Flows into third node. Number 6, where are you? Yeah, here's number 6. What's doing number 6? Flows into draw like this. What's doing number 6? Flows into number 4. Number 7, from 4 flows into node 3. Yeah. Who is the 8? 8, it's a motor, it flows into second from the base, and this one falls into 3 minus 1 0 0 0. Here it is. I'm rich. I'm have my topology matrix. What I need to do now? I need to I need to start some programming. Yeah. Can I do it? possible. Okay, I don't think I need this. Let's see if you will help to help. 1 second, I will switch my TV. TV. I hope it works. Yeah, something happens. I will take from line to ground immediately my Zeidel function. Anyway, I will need it. So this part is a magenta color. It's a Zeidel function to solve system of linear equation. I will end with this. Also, to work with Fortescue transform, I immediately put values for rotation factor a and a squared. I will need them. Next one, this one is definitely wrong. Let's fill our. What do we see? -1, 1, 0, 0, 0, 0, and 3 more zeros. 1, 2, 3. Looks correct? -1, 1, and zeros. Let's see. Okay, next. 0, -1. I need a slave to do this work. 1, -1. I definitely need a slave. -1. Or stop conducting them in real time, or just create a preset. Which one is next? 2 zeros. 0, 0, -1. 0, -1. 0, 0, -1, 0, -1, again, once more 0, -1, and here will be 0, and again -1. Funny pattern, isn't it? And next one, 0, 0, 0, 3 zeros, 4 zeros, 5 zeros, -1, and 1, 0, and 0. Looks okay? Really? Possible okay. Safely. Yeah. What's next? What do I feel next? EMF. I can use this part. I will reuse. Just written. What I have here? Transform factor. It's a reduction factor. I will reduct from 212 to 213 to 221. In reality, what will be here? Your middle voltage 204. This is voltage, let's say, area where I'm reducting. And this is from let's say, transferring. But before transformer, gray resistors and what? Yeah, and EMF. I will put them on a secondary side, on motors, on a large, nice motor side. Okay, next. EMF of the system. So EMF of the system goes with this reduction factor. And how many branches I have? I have 9, and here 2, 4, 6, 7, 8, 9. Really? 1, 2, 3, 4, 5, 6, 7, 8, 9. I have only one source here. In your real life, if you have distribution network with radial power, situation will be the same, only one source. If you have bridge between two substations, bridge line, so you will have two of them on each side of the bridge. And both should be multiplied by reduction factor. Yeah, what about resistor? This R1, it's a mimic for the middle voltage cable network. I said 5 ohms just for being a round number. But if I'm reducing to the secondary voltage, I need to apply a reduction factor in square. That's why I have a square here. Fault resistance, I'm not sure, but it's what written on the nice black resistor. 23.75 ohms. I don't know, it's 23 ohms. I have it here. Next one, I need data for my transformer. Here are date for my transformer. So I found it in some paper what during the short circuit experiment, voltage of my transformer at which current was equal to its nominal current was 3.8% of its nominal voltage. And losses 238%. So 2.5 kilovolt ampere, it's rated power with the very simple formulas, including what? Theorem, I got transformer resistance, and since I calculated it putting transformer nominal voltage to 130, it's a primary. I can immediately put voltage at secondary part. Just for clarity, I've calculated with the primary voltage, and here I perform reduction to the real this area of calculus. Also, my load resistance, these nice bulbs, they consume 880 milliamps at 221 volts. That's measured. Next one, I will need data for my asynchronous machine. Here is, we calculated it previously. I will just reuse. I need two resistance. One is a direct sequence. It's a bit trick. This 2.1 is no load resistance because I have no mechanical load in my machine. And this it's no load reactance. Because I use it, in fact it's a magnetizing circuit because it has no mechanical load and as a result very high active resistance on secondary side. This digit is for startup regime. It's XD. Longitude reactance. I have it. Now, what I'm doing, I'm conducting the resistance vector by branch. What's the resistance of the first branch? Resistance of the third branch is R1. Resistance of the second branch is transformer. Resistance of the third branch is RF. Branch number 4, it's a load. Branch number 5, against. Once more, it's a load. Again, a load. Branch number 6, L1. Branch number 7, transformer. Branch number 8, it's my asynchronous machine in direct sequence. Branch number 9, asynchronous machine in the secondary. First, I will do one moment what I'm doing. To show clear effect without asynchronous machine, I will multiply it by 10,000. It's just like switching machine off. I'm simulating action of the switch just by making resistance huge, so it will have no importance. Yeah. Here is my resistance. Matrix, what next? Next I need to solve what I need to do. I will reuse this part. What's in here? Number of branch, number of nodes, very simple inversion of the resistance matrix. I have network where all mutual inductance are eliminated. So matrix will be pure diagonal. Transpose of the first incidence matrix. Here I'm calculating nodal admittance matrix. I have no current sources here. That's why I vector is not present. I call my Z function to solve system of linear equation, and I will get voltages of my minute symmetric. Next, I don't think I need all these voltages. That's what I would like to get. I will copy this. What I'm copying? I'm looking for current going flowing through transformer. In direct sequence transformer is a second branch, it's okay. Here in negative sequence or reverse sequence it's a branch number 7. So I'm putting a 7. A phase current in a place of fault. This will not. This can work only. We can check this simple check, but this will show me a current of a load current. Okay, I will show how to use it, but it's very simple check of correctness. But in reality, it's not a current at the fault place. I will remove it. Yeah. Why I have a 0 here? Our fault is line to line, no ground connection. If no ground connection, no necessity to conduct a 0 sequence. So 0 sequence current will be 0 here. This I will remove it. It's only confusing. This one is good. What's this? What's a matrix? It's a matrix of inverse Fortescue transform. Here I have filled a sequence vector. If I multiply sequence vector with this matrix, I will get a real current. So I will get ABC currents of my transformer. My meters do not show angle. So to check with meters, I use an absolute value. Because my meters show absolute values. This part, I'm taking angles, but usage of arctangents here should be done, how to say, with precaution. Because arctangents in CLAB return so-called main value. For vectors like a square, and so on, it's a bit tricky. Okay, we can live with this. What should I do? I also will add code to get currents on the primary side. At this moment, I will get currents at 0.4 kiloohms. It's at a low voltage side. Now, Steve Irwin in crocodiles. What I needed, I need this code. I will make a copy. Here I should put a 7. What's going on here? When direct sequence current flows to transformer from the start to delta connection, and transformer has a connection group of 11, this current will rotate rotate forward by 30 degrees. If negative sequence current flows through such transformer, it will be subject to rotation in clockwise by 30 degrees. It's here I have rotation factor. It's a cosine and sine of 30 degrees. By multiplying with this factor, I will do what? I will rotate current in the second branch, which is my transformer in the direct sequence schematic, forward by 30 degrees. By dividing branch 7 in negative sequence, my transformer in schematic of negative sequence, current of branch 7 will be rotated backward by 30 degrees. And here you see division. I need to take currents backward from from calculus voltage step or degree or stage if you want to reality. So I need to perform a back reduction. This step. And next step, I perform a reverse Fortescue transform. This is reverse Fortescue transform matrix, this matrix. So I will get in phasors, and for measure I take absolute values to get magnitudes of current vectors. And also angles, but these angles will be, you'll see, I should be careful. Okay, let's put a save and let's calculate. Can we calculate? I'm not sure. Maybe, okay, it's don't know what it's 67. Oh. Lot in English, slodze in Latvian. So slodze Latvian is a lot, but it's too complex for machine. Here I have something. Look here, I have currents for BC fault. Yeah. Without motor, just flat load. Can we check it? Maybe it blows. Motor disconnected. What? Hey. It's important wire. It's a fault wire. Let's try 130 volts applied. load. Okay, one moment. I will switch my where's my go back here. Zero 90909 load current flows. Ground wire 0, load is symmetric. Can I do the fault? Fault circuit activate. A phase calculated 0848, yeah? 09. I can bring camera closer to my. Here. So, A phase calculated 0848 09. B phase 677 6.9. And C 674 07. Ground wire 0. Why 0? No ground connection, no 0 sequence, no ground wire. Okay. Can we add our tiny motor now? Or let's check primary. Let's check primary what we got. Here are my primary. Here are my primary data. So I'm seeing 3.9 in A phase, 7.5 in B, 3.8 in C. Angles are tricky. Yeah, I will measure with my clamp. Let's see what we got. Yeah. A phase 3.8. Set for 5 amps. A phase, where are you? Here, A phase flowing 4 amps. My meter shows 4. With the angle of approximately 70 degrees in leading, 70-degree leading. Here it shows 76. If we take a look here, what do we see? 09374. It's the first quadrant. Is it okay for 70 degrees leading? 09374. 1. Plausible for A phase. Yeah. Let's check phase B. For phase B, 7.5 in theory. I will switch for 10 amps. Here is my B phase, and it falls like this. I have 8 amps, 8, and angle of it's 95 lagging. 8 amps and 95 it's a phase B. Here, look, it's telling me 86. See this 86? But minus and minus. See this? Minus and minus means which quadrant? Third. Minus and minus. And if it's third, it immediately tells me what here, this 86 degrees, it's how stellar arctangles work. It's returned me 86, but it's a nearest angle. My approximation, what here I have 5 degrees approximately. But 7.5 and really 8, in theory 7.5. Looks nice. Smell of current. And in phase C, angle is approximately 95 leading. Approximately 95, it's a phase C. And its magnitude, C minus plus, looks like 95, yeah? And its magnitude for something like 4.4, yeah, approximately 4.4, not, should be in theory 378, but I am seeing 4. Approx 4.4 ohms. Interesting picture, isn't it? You see? It's on the primary side. I have one big current in phase B and two smaller, approximately 1/2 in A and C. What's going on? What kind of fault we have? B, C. Oh. But on the primary side, we see something more closer to B to ground, yeah? It's one of the best known tests for professional, let's say, fitness, for competence. If you have transformer, like 11 of first grade, with a 30-degree rotation, two-phase fold on a stack part, stack side, looks like L to G on a primary. Why? One minute. You solve this. Maybe my viewers also would like to see. Here, like this. Here's what we got in reality. Theory, theory, theory. Very basic theory without load. I have my load here. Without any load, it's very, very basic version. Only transformer and fold. Basic, basic, basic. I will see at the fold side something like this. It will be a phase sequence with ideal transformer at 90-degree. I will have the A direct sequence, B phase direct sequence, and C phase direct sequence. I obtain with 120-degree shift, and in opposite direction flows ideal negative sequence with something here will be negative sequence B phase and something like this negative sequence C phase. If I sum them, these two will produce 0. So A phase current will be 0, and sum of this will be my B phase in ideal case, and something like this will be my C phase in reality. We got 1 second. Where is my... Oh, look at that. It's our... We have... What's this current? 0.84. It's a load. My bulbs. And with addition of load, see, B phase. Minus 78, minus 773. Down with a small angle because of load, and C up, but also not, if no load regime, it should go ideal vertical, but it's with some angle because of load current. This is easy. It's on the fold side, on the fold. But when we look at the primary side, we see something different. I can erase this. What we will see? Direct sequence current rotates forward by 30 degrees. It's direct sequence. So B phase of direct sequence will go down, and here will be third phase. Swap. For negative sequence, we will see backward rotation. approximately like here 30 degrees. It's A phase of negative sequence. B phase goes vertical and like this should go of third phase of negative sequence. Something like this. If we sum them, what we will get? We will get double B phase and sum this one, and here I will have this plus this gives me current of the C phase, and this plus this will produce something like A phase current. 1/2, 1/2, 1. It's an ideal case. In our 3.8, 3.8, 7.5. In theory, in reality it was 8, it's big difference. But again, this is not, this is close to truth, but in real life you can also have an asynchronous law. What's the difference? Asynchronous machines have low resistance for negative sequence. Let's take a look. One moment, I will alter my program. I will, hey, I would like to put small change in my program. Here I use 10,000 to switch motor out. Now motor will go in. Calculate. Yes. Now it's my asynchronous machine. Not so nice picture, yeah? Not so clear. One small and two big. See the difference? Can we do it? Let's first tackle currents. So my calculus show 3, 5, 6. Strange, isn't it? Let's see. What activated? Fault. Previous 0.9, 6.8, 6.8. Pure active fault. Will it start? Asynchronous machine active. 3 amps in A phase, 301 calculated. 5.72 or 5.62 in B should be 5.26, big difference. And 7.4, 6.9, bit asymmetric. But close. See what point? Asynchronous machine takes negative sequence to itself. It's a small resistance for negative sequence. Now what will be on the primary side? On a primary side, we should see 2.8, 6.61, 5.15. See, no longer too small and large. Because blue part, this part is much smaller. It's let's say sunken by asynchronous machine. And here we are, A phase. A phase has a magnitude of 3.2, should be 2.8, I see 3.2. Its angle is something like 35 leading, 37 leading, possible. Phase B. In the phase B, magnitude is what it is 3.8 by 2, 6, 7 points, something like close to 7, and its angle is 95 lagging. Angle 95 lagging. And for C phase, its amplitude 6 amps. Here I have 6 amps. Bit bigger. It's and here something like 105 leading. 105 leading. See, it's near, but this small, this nice distribution, too small and one big, no longer in force. Because asynchronous machine took negative sequence. What can we also do? We can calculate a lot more. Oh, BGV. One moment I would like to show. One moment I'd like to show. Make it closer. I will take measurements of asynchronous machine. My asynchronous machine. Let's try to see. Voltage applied. There is the A phase. This should be phase A. No fault. And A phase 1.4 amps. Fault regime 2.6. What's it? I'm adding fault BC. But motor's A phase current increases. Why? You see, motor's current at A phase increases. Why? Because this non-symmetry, in our theory, it's a negative sequence, starts flowing through motor. It's addition what brings in negative sequence. For the B phase, phase, I'm measuring phase B. You see, current increases. Voltage decreases because it's a fault. You see, lamp, but current increases. And on C phase, I'm measuring phase C of the motor. You see, current decreases. Because it's a negative sequence, it has an opposite phase sequence. When negative sequence current flows, it transforms this real current. Of course, there is no zero sequence. In reality, you have some part of a synchronous machine at your customer. And this also brings additional complexity. The currents you will see in reality, they are close to this theory, but not exactly, because negative sequence will flow to the primary side only partial. Part will go to the customer, to the client's asynchronous load. Or if there is a, let's say, cogeneration plant, negative sequence will flow to this plant. But if, for example, they have solar system, such effect will not be observed, because solar system's inverter will not pass negative sequence through. It's important. Yeah, and what on the primary side? Expression on the primary side. And what should I do next? Maybe let's try to find in theory what will be currents of the asynchronous machine. We remember number of branches. Let's try to obtain this motor current. Its branch number, which one? Seven. It was 8 and 9, yeah? 8 and 9. What do I need to get them? First, I need, let's say, I can take this, I will copy it here. It will be and 8 and 9, no zero sequence. 8 and 9 or not? Yeah, it's okay. 8 and 9. I also will copy this. On. Motor, see motor, motor, motor. motor. Asynchronous machines. Asynchronous machines. Asynchronous machine. Asynchronous machine. Blah. See how it's easy. On take currents. We already solved all network. Just apply, conduct sequence vector. Use this beauty of inverse transform and save and execute. And what are we seeing? Aha. So currents of motor should be 3, 5, 6 amps. Widths, angles are strange. Yeah, you see deformation. A phase positive. A phase goes down. You see 236 in real, but minus 187 down. B phase, both minds, it's like this way, so whole star rotates, and it's a clear clearly deformation. But am I applying 1 second? Did they all have direction up? Both, in both, yeah. I erased schematics. Both motor branch were directed upwards. See? What? 3, 5, 6. One moment to Google. It's not energy. Let me do my job. Power applied. Motor on. Force active. Now A phase. Looks like this one should be 8, and it shows make 2 point something. It's like 2.5, 2.6. Should be 3. Maybe okay. So this one should be phase B. Let's check. And it's magnet, it's small. It's 2 ohms. And here, in theory, it's a phase, but it's small. It says 5. Yeah, and it's not correct. It's only changes rotation, direction of rotation. It's not the problem. It should be what? It's a C, it's an A. Yeah. A.
Yes.
One should be, we should see one big and two small. I think this one should be different. Symmetric. Let's check angles. A face, no walls. And angle. Not 80. 80 and lagging. Okay, 80 lagging. For the beams, 160 and leading. 80 lagging. Down like this. 160 in lead. Because here we have an opposite phase sequence. And for C phase, 40 and leading. Oops, we have an opposite phase sequence. Angles are not, we have an opposite phase sequence. Mobile. Yes, go. My son, current falls this way. And here it is 8, approximately 80 lagging. No more, it's normal because we have no more regime here. 80 lagging for A phase, it's okay. Oh, what? Current falls, it's okay. Actually, not current falls, but energy falls this way. Yeah. Yeah, and but same to zero. Yeah, you will see it opposite. No, see, it's same, but when you have a correct reading indicator and the scale goes synchronously, see? Goes to right, goes to left. And in incorrect, in mirror direction, they go opposite. Should go in one way. So 80 degrees, it's okay. If the phase B, let's say 80 degrees over this. Phase B should go to the negative. It involves its start. I see one counter. 60 leading. It's not okay. 160 leading, but A is 80. What? So, I need from 120 take off 80. Why from 180? B phase was here. Was originally this way. So from 980 I took off 120 and remain 60. Go up this and I should have 20 degrees here. 20 degrees here minus 160. Yes, it's phase zero, it's okay. And for C phase 40 leading C phase original was here at 120 minus if you rotate by 80 degrees it will be 40. Yeah. We have a star rotated to 80 degrees. And now with the flow we see something in local. 5 points. 2.5. Small one at C phase and 2.2 at B phase. Something wrong here. Something wrong. Where am I wrong? Where's my mistake? I made a mistake. I need to find it. And it's here. What 8 and 9? It's correct. But what about signs? Really 8 and 9? Really 8 and 9? No. Yeah, it's okay. Really 8 and 9. Should not be like this. No. It's really 8 and 9. That is my Of course I'm getting the results. Am I an idiot? Take a look what I'm doing. I conducted vector, but what I'm put here, it's a serious problem. Hey, here are my currents. 249, 239, 059. I find a mistake. I use sequence current, not a motor sequence, vector. I found a mistake. Here at this point I forgot AM error put in. So I used the sequences of the line, not the motor. It's stupid. Stupid mistake. Oh, let's check once more. It's a very stupid mistake. Let's check once more with my motor. We should get 249 in A phase, 239 in B phase, and 059 in phase C. Let's check. It was stupid. And sorry, motor goes A phase. 2. Should be 249, 2.5. Yes. 2.2 instead of 2.4. And C phase. 0.8. No, it's not 0.8. 1 second. It is 3.4 multiplied by 2, 6.8. 0.6. 0.68. And okay. 3.4 multiplied by 2, it's 6.8, 0.6.8 instead of 0.6. Now it's correct. Stupid mistake, sorry. Now okay. I made the mistake in program. I took wrong vector for the inverse transform. This should be compared, and it's mistake. Only thing you can believe when everything is absolutely unclear, build a vectorial diagram. Now values are they are close with reality. No flying models. Now it's correct. Check later. What part of negative sequence our motor took? It's one second. For the it's 7 toward 8. Let's check. Sorry, 9 divided by absolute value of 7. Yeah, 7th is my transformer. Yes, 7. Wow, look at this. 70% of the negative sequence go to motor. In magnitude. Through motor flows 1.69 amps of negative sequence and 2.3 goes to net. So motor is 70% of the network. Quite significant thing. Yeah? Okay. You saw it. Be with me. Sometimes it can be, let's say, check for your professional competence or fitness. Exact such kind of fault. In pure reactive load, you will see very nice picture. One big current and two small. What should you do? How to say it's a fault on a client side or it's something strange in distribution network? What's the difference? What's present in earth fault and not present in one-to-one fault? Ground current. First thing you need to check is a zero sequence voltage. If zero sequence voltage present, we see an earth fault. For example, here in rig, at earth fault at 10 kilovolts will have magnitude of 1 kiloampere. It's done artificial because we have low earthing for distribution network here. So it can be one large current because of earth fault in the network with low grounding, or because of fault on the client side. What you check? Zero sequence voltage. If it's present, we have a earth fault. If not, we see what I'm modeling. This can be quite significant. Okay, I think I I spent my time for today. Yeah? So I can